Hello, this is an introduction to probability and statistics. It's part of a class on modeling and numerical methods at the University of South Carolina. We're going to do a lot of stuff with Excel. So in general, Excel is a good software tool because it just solves a lot of problems and it's very useful in a lot of different ways, and it's available pretty much everywhere. Most of the things you can do in Excel, you can also do in things like Google Sheets online. But Excel has a few extra tools, especially for statistics and engineering, that are a little more useful that I haven't found comparable tools in some of the online options. So there's uncertainty in everything. So real systems have uncertainty. This is from a paper I wrote years ago on granulation. So how to predict how particles agglomerate into larger particles or how they break. And you have to deal with uncertainty when you're doing experimental applications. So in a real process or a real system, you're going to have graphs, and your graphs show data, but you need to be able to quantify uncertainty on the data because you never get the exact same measurement over and over and over and over. There's always noise or uncertainty due to a lot of different factors. So you have these error bars, and it usually shows the average value and the standard deviation, but there's different ways of using error bars too. So you have to be very clear when you're presenting data what you mean by error bars. So probability and statistics. This was a confusing term for me, just the two different terms. I thought they were basically the same stuff. So your probability, you may have a distribution of uncertainty for your process, and it has parameters that dictate if you have what your overall uncertainty in your process is going to be. So if you pull out a sample, you can't sample the entire population. Like if you're going to roll a dice, you can't roll the dice for every single combination. You sample, you pull out, if you're producing TVs on a production line, you can't sample every TV to see if it works. You pull out one or two or five or whatever your number is, you get a sample and look at the quality of those. So that sample probability lets you predict. If you know what the population, if you assume you know what the population is, probability lets you go forward and say, what kind of samples might we get? Is it going to look like a nice normal distribution or some other distribution? So that's going from, we know the model and we predict what it's going to do when we sample it. Statistics is backwards. You given a sample, you try and back out what the population looks like. So you sample the system. I used to work at a paper mill. We cut pieces of paper. We wouldn't take the entire roll of paper that we make. We'd cut a few pieces, like 1 foot by 1 foot samples, and test the strength. And then we try and figure out if that's, assuming that's representative from the full population or the full piece of paper that we're producing, that's our sampling and statistics. So your experimental design, that's another thing that pops up into probability and statistics, and that helps you decide how to do your sampling, how to pull out values from your process, or how to do that experiment to actually grab the values that help you get a good statistical representation. Variability, so precision and accuracy are two terms you're going to hear in science. You can be very precise and give you the same thing, but it might not be the right answer. You can be very accurate because you're centered around the target, but it's not very precise. What you'd like to be is precise and accurate. And data is going to have variation. Your process variation comes in from disturbances, things out in the process that are whatever experiment's going on. Your population, if you're doing biomedical applications, you have sample variation. You have noise in your measurement device. If you step on a scale every morning, it's going to be off a little bit. It goes up and down, things change. Some other external forcing, which means other factors beyond your even comprehension. You may not know that something going on, but it's going to just affect your process. So we treat values, measured values, as random variables in a lot of cases. You don't actually know the true value, but you make estimates based on the sample data that you get from your measurement device. So you probably know mean, median. You should know this. This is, I think, middle school or elementary school. Add them up, divide by the number. Mean is the average value. Median is the one, if you line them up, the lowest to highest is in the middle, or it's the average of the two in the middle. So mean and median, make sure you keep those straight. My son said it showed up on the SAT, so they'll check you and make sure you know the difference between mean and median, probably mode as well, which is high frequency. The biggest thing you should be familiar with is histogram. So when you have a random sample, say you have test scores, so you put them on a distribution. You don't show every individual group, you put them into bins, and then you count how many of your measurements show up inside a bin. So it's a frequency, basically. So if you have 1,000 students taking the SAT, you could line up all of their scores and put them in groups of how many points on each session, and you look at how big or what that shape is. How many were really high, how many were really low, what's the most frequent one, the mode, show them the average maybe. And there are suggestions on how many boxes or bins you should put together depending on how many samples you have. So if you're assuming a normal distribution, which is a bell-shaped curve, you can sample. So eventually this sample for 40, let's see, if you have 40 samples, it doesn't look like a bell-shaped curve. But if you go up to like, what is this, 10,000, there are some tails on the low end and the high end. For a proper bell-shaped uniform Gaussian distribution, there's a probability, even if for this example where I was sampling average 50, and I think it was plus or minus 10 with standard deviation, there's a non-zero probability that you have somebody getting 0 and somebody getting 100. There's actually, it's not a limit on this. In this example, with a Gaussian distribution, you can go above 100 and below 0. So the one thing to remember for Gaussian distributions is that if you're around the middle and you look at plus or minus 1 sigma, it should include about 68% of all your data. So if you kept running this long enough and you calculate the average and the standard deviation, it will capture 68% of the students on your test score, if it's a Gaussian distribution. It's not always a Gaussian distribution. We'll talk about that in a little bit. So standard deviation, you get your average value, mean value, and you go through all of your samples, all of your actual measurement values to get the variance, divide by n-1. So if you have 100 students, you divide by 99. Standard deviation is the square root of the variance. And the standard error of the mean is the standard deviation divided by square root of n. And I've seen this used in biological systems because standard deviation can be very large, very significant in biological systems. So if you run the experiment over and over, you can divide by square root of n to report the standard error, and it looks less, like you have less variance, but you still have a lot of uncertainty. So basically, S is what we use for the sample standard deviation when you're taking data and calculating it. And the ideal, remember probability versus statistics, sigma would be the sample deviation. But a lot of times in engineering, we'll use them interchangeably just because we abuse notation a lot of times in engineering. But science, they might be a lot more picky for you. So you need to report your sample. That's something I talk to students, like for science fair or experiments. You always need to tell how many times you did the experiment. You can't just do it once and say that's the value. It'd be great if you could, but you can't. There's a paper out there, there's lots of papers out there that look into distributions and trying to, see if data means something, correlation and causation. And this paper from a while ago said that the male and female for the certain test at a certain time in a certain sample, a certain group, they basically had the same average. But the boys had a bigger variance, which means a bigger distribution. So they have the same average, but longer tails on this test. So that means that on average, the boys and the girls in the test were on the same, but there were bigger tails on the male side. So the variation was a lot more, which means there's a bigger chance at the higher end that there are more boys on this test doing well, but there's also on the other end, a much bigger chance that there are boys doing very poorly if it's a nice symmetric distribution. But again, any intelligent test is very, very prone to error. What does intelligence mean? How can you measure it with one test? So on this one test, you can say that there was a difference between the boys and girls that took the test, and the variation showed up. So the populations are the same average, but different standard deviation. The biggest thing I want students to think about is how to quantify systems, or probability distributions. So if you're thinking about a random variable, a lot of things are continuous values, like weight, concentration of a sample, temperature, velocity, pressure. But there are some random values that take on discrete values. So if you're manufacturing something, how many failures per lot? You make 100 a day, how many failed today? How many failed last week? Or points in an exam, you don't usually have a continuous value for points in an exam. Or how many times you've actually successfully completed a product. So these discrete values versus continuous, that's one way, and there's different distributions to use in different cases. Not everything is just normal. So there's also limits on the feasible range, like concentrations can't be negative. The number of failures in a lot, you make 100, how many failed? It can't be negative. It can't be more than 100. So there are limits on your range. Like a mole fraction, if you have a fractional concentration between 0 and 1, there are distributions specifically for 0 to 1 ranges. So continuous versus discrete, and also the range of the variable help you determine, if you're going to do some probability modeling, what probability distribution to be used. One that we're pretty familiar with, you should be if you ever played any board games, is rolling a die. Single six-sided die. It's going to have a 1 in 6 of any of the numbers. It's called a uniform distribution. So it's discrete. You have the same, as long as you don't have a weighted die, have the same probability for the frequency should be equal for all of them. So sometimes we talk about the cumulative distribution function. So if you go through all the values that that die can take, if you, from starting at 0, there's 0% chance of it being 0. And out here, when it goes to 1, that means it's a 100% chance of being somewhere between 1 and 6. So basically, a cumulative distribution function is the integral, or adding up all those values under that curve to give you a value. A lot of times we just look at, basically this is like a histogram. If you roll the die a million billion times, it should be exactly 1/6 of the time 1 and 1/6 of the time 2. So that uniform distribution depends on the lower and upper limits. Your continuous uniform distribution might be like a mole fraction, somewhere between 0 and 1, and it's any continuous number between the lower and upper limits. So your probability distribution is, again, just like a rectangle. It starts at A, 0, there's no value below A and there's no value above A, but there's an equal chance of all the values in between. And the cumulative distribution function would be the integral of that line, which basically goes from 0 to 1. For your Gaussian distribution, like I said, the tails go to infinity. You need the average and standard deviation. You can do this in MATLAB very easily to make these kinds of charts and graphs. This is the underlying function that defines that nice bell-shaped curve. You can see that the average shows up, standard deviation shows up. So that's the underlying value to give you this distribution. But again, even for MATLAB, for low numbers of samples, you may not get a nice bell-shaped curve. You got to kick that number up to make it start looking more like a bell-shaped curve. In some cases, you take the log of a random variable and you plot those on a histogram, and you get different distributions. So again, it's just standard deviation and average again. That's all you need to describe that system. But depending on the values you get for those, you might, again, 0, because you're taking a log, it can't be below 0, but it can have long tails. You get different shapes of those histograms or probability distribution functions. The Weibull is a different distribution. Basically, if you're looking at failure rates of something over time, you might have a failure rate that decreases or stays constant or increases. So those failure rates, it's like time to failure. How long? It's a continuous distribution again, but how long is your product going to last? Is it going to fail early? Is it going to fail later? And you can have different distributions looking at your sample of how your product works. Again, you can make MATLAB code, and depending on these factors that show up in the distribution, you can actually calculate back, or they relate to the average and standard deviation. So again, average and standard deviation characterize this distribution function. Even though you have a failure rate and scale factor, those are what you use when you're talking about it, but they can be derived for average and standard deviation. Beta function is another one. If you're looking at mole fractions, you might use this because it's ranging between 0 and 1. So there's just different continuous distribution functions. And again, if you have the shape factors alpha and beta, there are functions that relate to average and standard deviation variance. So going back and forth between those two values. So again, it's why if you see this pattern, average, standard deviation start to give you characterization for your distribution, even though you might get different histograms or different probability distribution functions for your different distributions. You base that on the continuity versus discrete and range. And there's lots of different continuous functions out there. Some other ones that are interesting, if you get into Fisher and student T, chi-squared, those are ones that show up in probability for using a lot of the testing. We'll talk a little bit about student T later on for hypothesis testing. So in the discrete side, if you're doing discrete distributions, binomial distribution is one that's interesting. If you have yes-no events, like flipping a coin, and there's a probability of a success, and you do this enough times, for large N, it's basically going to look normal. So for, I think there's 100, and with this line in the middle, it's 50% chance. So it's an unbiased coin, you run it 100 times, you know the average should be around 50. And it gives you non-zero probability that you will always do heads and tails. So you can calculate what's the chance that I flip that coin 100 times and always get heads or always get tails. But if you weight that coin, you can weight it on either side and get different distributions. So it's, again, true, false, discrete values. This is more like a test. If you had 100 true, false questions on a test and you're totally randomly guessing, you should have this nice little distribution where most everybody's between 40 and 60. And again, average and standard deviation relate to the parameters you use to describe this distribution. So those are the important parts for the binomial distribution. True, false tests, number of events given so many trials. You can think about it in terms of roulette. You've got 37. How many times do you play? Payback is 35 to 1. So if you're doing probability of winning is 1/37th. And how many times are you actually going to bet? So that you can start to analyze. That's a lot of probability started because people want to look at analyzing gamble. Son distribution is one. It gives you number of independent events occurring over time. A good example is how many letters per day you get on average. So you might get 4 letters a day, but it could be anywhere between 0 and whatever, 10. So 0 to infinity is the range. It's discrete again. How many of things, values, show up, and they're totally independent. Receiving one letter has nothing to do with how many other letters you get on that single day. But the average and variance on these are both the same. So that's a relationship, that lambda factor. You only have one lambda factor for that Poisson distribution. And again, there are lots of discrete distributions for different applications, different underlying functions. And they give you different shapes, you have different parameters you can play around with. So you can get into that if you're really into probability. There's a distribution tool in MATLAB. If you want to play around with it, you can play around and look at what the distributions are and look at the different parameters that characterize distributions to see what they are. It doesn't give you information about how they're derived or what they're useful for modeling. One thing you might run into is a box and whisker plot. This is another way to represent data that's uncertain. So for a single experiment, you have the minimum data value, the maximum data value, the top quartile, the bottom quartile, and the median. So you get all of those values, 5 different pieces of that distribution, all together on one. It's like error bars on steroids. So you get a lot of information. So it helps you characterize. So you know that inside this box, if you did the experiment, 50% of your data should be in there. So it helps you quantify those values. And it's good for small data sets. So you might end up using box and whisker plots, potentially. And MATLAB is a good tool for making those very easily. It's real hard to do these in Excel. I've seen people try, but it's sort of a mess. Like I said, sampling is important. If you're sampling of your data, you need to have a good sample. And this is especially important if you're into uncertain systems that involve like biology or people. So your random sample has to be truly random, and a lot of times that's where a lot of experiments fail because you're not really sampling randomly. So sampling errors, if you're political polling, if you call landlines, that's not everybody has a landline these days, so that's not the best sample. Reporting bias, if you change how you're doing testing, changes in autism rates, and people have attributed that to changes in the actual diagnosis methods or standards. Paid clinical trials, selection bias. You pay people to test out drugs. So you're basically people that are economically disadvantaged, like college students, that are really need money, so that might get a different population than actually just randomly selecting people out of the general population. Interesting one was people looking at airplanes, and they would come back with lots of bullet holes, and they plotted those values, and those values were used like trying to decide where they wanted to armor the airplanes. Well, it's not a good selection because a lot of the airplanes were not making it back because they weren't truly random. They get shot down in World War II. So you start realizing the spots with low damage, like the engines, the fuselage, the wings. Those are probably the places where you need to armor the airplane additionally, because those airplanes are not making it back to report on damage. And so it's the same thing with, I've heard the stories about the first time they started using helmets in combat. People are coming back with terrible head wounds, but it's not a good sample because previously, before they used helmets, those people would get hit in the head and not come back to get helped out. So sampling, it's not a truly random sample in many cases. Like I said, statistic is a function of one or more random variables that does not depend on unknown parameters. And the one we commonly use is basically the average. So you know the number of values, and you can sum of them divide by n, so that's a nice statistic that we commonly use. If you don't know the parameters, if you don't know the average and standard deviation, that is not a statistics. So your confidence intervals from a normal population can be calculated. You have these parameter values. So if you have a confidence interval and you set this alpha value, and our alpha value, usually we set it at 95% confidence interval, which means alpha by 2, or alpha would be 5. If 95% is our confidence interval, and that means alpha is 5%. So we're looking at a two-sided test where we have 5% of our data, well, half of 5, 2.5% up here and 2.5% down here for symmetric confidence intervals. So 5% of our data is outside of these bounds, assuming our data is nice and Gaussian and it's sampled. And when we take those, that means that we can say how much uncertainty. It's sort of like standard deviation. And it makes sense because when you put that in there for a known standard deviation, if you assume you actually have a good value for standard deviation, you know how many points you have, you can quickly quantify your confidence intervals around that average value if you know the standard deviation. One of the examples I like to talk about is this example where they took 20 tests. They ran the same test, and the 20 tests over and over, and you have the average. And what the confidence interval really should mean is you're confident, you're 95% confident that that captures the true average. So if you know the true average is 40 and you ran the test 20 times with a 95% confidence interval, that means 19 out of 20 times the confidence interval should capture that true value of 40. In this example, there are 2 unlucky experiments out of the 20 that did not capture that average value. So that means again, it's 95% confidence. If you ran it enough and you know the actual standard deviation, you run that experiment, you would expect 5% of your experiments to not capture the true value. That's what the confidence interval means. So the central limit theorem, basically, as you take more and more values, you're going to get, with a nice statistic like average value, you're going to get a nice normal distribution. So as you let n go to infinity, that statistic is going to, your sampling is going to follow a normal distribution. So that means you're going to get a nice standard deviation, and you can measure these values for larger n's. If you don't have a full distribution, or you don't have a large number of n, large number of samples, you use the student t distribution, which is slightly different from a normal distribution. It ends up having wider tails, so you have a little more uncertainty because you have a smaller sample size. So your student t distribution looks normal, when you're trying to quantify the average value. So you get your average value from a measurement, you do this a few times. Your student t will give you bigger confidence intervals. So you have to use a t-distribution, which depends on the number n of samples. And that confidence interval will be slightly larger than if you're using a Gaussian distribution. So getting into hypothesis testing. The null hypothesis is the main thing you focus on. So you have a status quo hypothesis to be tested, that nothing has really changed. There's nothing novel about your two data sets if you're just doing comparison. And you have an alternative hypothesis that something interesting has happened. So we're trying to collect evidence if we can reject the null hypothesis. It's a different way of thinking about testing. You're not trying to prove something, you're trying to prove something false. Null hypothesis is false. We have enough data that sets A and B are statistically different. So the null is just like the average is the same as between the two sets. And the alternative is that maybe it's a one-sided test, that B is actually greater than A. What we're really trying to do is say that B is, the average one for the test B is greater than A, but we start off with the null hypothesis that they're really the same, and we're trying to collect data and show that that null hypothesis breaks. So you have a test statistic. You're going to sample the data, and you're going to have to decide whether or not to reject the null based on that test value. And your critical rejection region tells you if we have limits on our uncertainty, and it will push us into certain regions. And we have to set our alpha value again, significance level, like 95%. Do we want to be 95% certain? So that's the limit on rejecting the null when it's actually true. So what level of mistaken test do you want to? It depends on your application. 95%, or is it 99, or is it 5 nines? You can set different values for the critical region. So how much of a difference do you really need in the test? How certain do you want to be that you don't make a mistake given data? And that alpha for a one-sided test would just be, if you have your distribution, your limit is going to be out here somewhere in that distribution, depending on how much your alpha is, 0.05, 0.01, depending on how much potential error you want to put up with. So one of the examples I like to talk about is the truth is that if you're trying to judge somebody guilty or innocent, and you either accept or reject them. So the null hypothesis is that you presume they're innocent. So you presume they're innocent, so you let them free. The correct alternative, if you have enough evidence, enough data, you can reject the null hypothesis and find them guilty, and that's good if they're actually guilty. But there are two types of errors to deal with. Type 1 error is incorrectly rejecting the null hypothesis. You put an innocent man in jail. And type 2 is the other one, where you miss a guilty person and you let them go free. So that's when you start talking about hypothesis testing. You set these values for uncertainty, you look at your data, you understand your experiment, and are you going to say it did happen, or you might still make mistakes depending on your experiment and your distribution and your alpha. So the type 1 error is called alpha risk, and your probability of type 2 error is your beta risk. And that's when you accept it when it's false. So alpha and beta are two different types of error, and you can quantify both of these. So power is the probability for rejecting H0 when it's true, and it's 1 minus beta. So you want a good powerful test, which means you split the two populations between A and B very effectively. So you have these decisions, true and false. The correct decisions are to say they're the same or they're rejected. Your alpha risk is the producer's risk. If you have a shipment come in and you test it, and you have a test and you say, okay, even though I'm null, it's good stuff. The bread comes in from the bakery and we test so many loaves and we have our test and we look at our quantity and we say, we're going to reject it. This is a bad shipment. So you're rejecting good product coming in. You are putting the innocent guy in jail. That's your alpha risk. And you can set that based on your own testing for your population for good, if you have enough good samples. And the beta risk, if you have enough information, you can start to quantify that. It's consumer risk. So it comes in and you measure a quantity, it falls below your limit, your quality control limit, and you say, well, if it was out here, we would reject it, but it's over here. And so we have to accept it. So the consumer accepts a bad product. Your bread comes in, but it's actually going to go bad and you're going to have to throw it out. So that is the beta risk. So these are the two different populations. Visually, you got one population that's good and one population that's bad, and they can have different distributions, so they have different averages and possibly different standard deviations, and there's some overlap. What you'd like to do is have a better separation between your populations. So a different experiment, a different way of collecting data, so that you have a very discernible, there's very little overlap between the innocent and guilty. So you have a very good test, and there's very small room for error between alpha and beta because you have good separation between your averages and there's not a lot of variance. So it's a much more powerful test if you can develop systems where you have the innocent and the guilty very highly separated with a clear delineation between the two. Of course, during quarantine times, we have to talk about zombie pandemics. So it's the same thing as locking you up. If you have a test, and you can run that test on healthy people, run that test on unhealthy people. And the truly good people that aren't sick should be free. And the other, you have to quarantine the ones that come up as a zombie. So that's what you want to do. And then we're trying to quantify type 1 is putting the people that aren't sick in quarantine. And type 2 is that beta risk of letting people that are infected go free. So it's the same thing. You measure, if you have your test and you have these two different populations. The null hypothesis would be healthy, uninfected, and the alternative is they are infected. And then all this hypothesis testing is about sorting out how do you quantify between the two. So you have those limits for type 1, type 2, alpha and beta. And P is the small value. So when you get a sample, it gives you some indication, your p-value, where you are on your null distribution. So if you get a value way out, if you get a sample out here, it's very, you might, in this case up here, the p-values be very small because your sample puts you very much into the zombie side of things, like they have a very bad test. So that p-value indicates, if you were on this distribution for the normal distribution, for the null hypothesis, the p-value tells you how far out on the tail you are. So a small p-value usually means that you are way over into the alternative region. So you like have a small p-value. So the p-value is the probability of obtaining a specific test statistic more extreme if the null hypothesis is true. So how you'd like to be beyond your test statistic. So you may have a test statistic that tells you your alpha value sets up what Q value is. So that sets what your limit is when you want to decide between is it null hypothesis or is it actually the alternative. We're going to accept that. The P value gives you the probability of observing a specific sample, more extreme. So for the null hypothesis, that means there's a very small chance that we're way out in this tail, which means we probably need to jump onto the alternative hypothesis. So if the P is a very low value, the null is going to be rejected, and we're saying we've got something interesting. Our data shows statistically we've got some good information. So you can have average value, and then you get a sample. So this would be a large p-value. So we have set our alpha values. So for two-sided tests, we're looking at differences between two values. But you get a sample, and now because your sample is pretty close to the average, it's a large p-value, which means based on our average for the null hypothesis and the standard deviation for that, it's probably null hypothesis. You can't reject it. It's pretty close to the average, to the what we think is the true average. But if we get a sample that's way out on a tail, for the null hypothesis, there's a big difference between the two. So we're going to get a very small p-value because the normal distribution, there's a very small probability that you'd be more extreme if you're pushed away. So large p-value, you can't distinguish. Small p-value, you can distinguish. There's something going on between the two different tests, or your test is indicating something interesting is happening. I'm going to mention regression. If you have data, a lot of times we make a linear regression. So basically, for the simple case, it's another part of statistics. We take data, and for the linear case, we're looking for slope and intercept. So we may have some independent variable we can change, like the temperature in the reactor. We collect data for a bunch of different temperatures. We measure the concentration. So that, to make a linear model, if we do this for enough experiments, we can start to change those values and get a linear regression for slope and intercept. We don't just do 2 experiments and draw a line. We usually run the experiment multiple times to get a good fit. Now there's also an option for multiple linear regression where you're looking for these parameters, B0, B1, so you can have lots of parameters. You can include more parameters, and what you're really trying to do is fit a plane or a hyperplane through your data. So you look at change of temperature and the pressure, and then you try and model the concentration in your reaction. Assuming it's linear, you're trying to find the best values for your parameters. You can do linear regression in some other cases if you know temperature and pressure, but your model, you think it has a nonlinear effect with temperature squared, or because you know the x values, you can set this up in a nice, relatively linear way. So it's it looks like a nonlinear model, but it's really, you're finding linear coefficients because of the way the coefficients appear in the expression. Now, if the coefficients appear in a nonlinear way, you can't do that. You have to resort to nonlinear regression. But there's a lot of applications for linear regression. Usually we're just fitting one parameter, independent-dependent relationship, so it's a nice simple line. But there are cases where you use multiple. And if you know something about linear algebra, you can set this equation up over and over and over. You basically take your model and you know your y values that you measure and your x values for like temperature and pressure. You put those values into a set of equations. You've got 3 unknowns. If we run the data 4 times, we have 4 experiments. So you have your values for x1, x2, x3, x1, x2, x3, x1, x2, x3, and all your y values. You set this up with, in this case, it's only, actually, I'm sorry, it's 4 unknowns and 4 equations. So it's a perfect square. You can solve that, but typically you're going to have a lot more data. You're going to run more experiments because you like to replicate your data values. And if it's a 4x4 system, you have 4 unknowns, 4 equations. You can find the matrix inverse, solve that exactly for your parameter values. But when you're overspecified, you run more experiments. You end up with maybe 1,000 data points and 4 unknowns or 3 unknowns. The more Penrose pseudo inverse allows you to calculate the best fit for your data. Something you'll run into when you do regression is a correlation coefficient. You have basically a Pearson's correlation coefficient, R squared. It'll pop up on your Excel data sheets. The R squared ranges from 0 to 1. 1 is a perfect fit. Your data is exactly on your line. If you ever see anything close to 1, it makes you nervous because that means you're fitting the data. You don't usually do it by hand. It's somewhat an intricate calculation. It'll pop up on Excel graphs if you ask for it's very easy to get this out of Excel and some types of regression. But your correlation doesn't imply causation, but it gives you some indication of how good a fit your data is to a nice linear model. So 0.95, 0.9, even 0.8 in some cases is pretty reasonable for there's a relationship between this x value and this y value for our linear. Another thing you should be aware of is interpolation of data. If you have x and y data, you don't know the model between them. You assume it's linear. It's basically just using the function of a line for assuming between 2 data points, you're going to interpolate between them. So you know the y values on the left-hand side, and you know the change in y values, and you know the change in x values. You're assuming you're evaluating this at a point x. So your function is just basically you're doing a line between 2 points, and you're interpolating between them. So if you're trying to value this at 4.3, you're between 4 and 5. You have data for 4, you have data for 5. So using these two y values, final minus initial, and these two x values, final minus initial, that gives you your slope. This is your change in the x direction from the left-hand point, in this case 4. This is where you actually are, so that's the value you're interested in. In this case, it's nice to remember that 4.3 is closer to 4, so whatever value you should get should be closer to the value correlating to 4 than to the other side. So it's basically just interpolating between those two. You have to be careful when you use interpolation. You're assuming a linear model between the 2 points, but it shows up in a lot of engineering applications. So like I said, if it's closer to one end, the resulting value should be closer to that point, but not exactly on there. And it should be between the 2 points too, so don't make mistakes. Interpolation should be in between them. Extrapolation is really dangerous, but sometimes we do it. So if you're going to extrapolate off the ends of a line, we'll look, if we have f of x, if we want to find the value of this function, we only have data for x between 1 and 10. If we want to find a value at 11 or 0.5 outside of a range of data, it's called linear extrapolation. Again, you take the last 2 points and you assume that your linear model shows up between those last 2 data points. Use the same expression. The left value y, the left value x, the right value y, right value x, and the change right between the x's. So again, extrapolation, if we're looking at this last point, we're going to use points 9 and 10. So those 2 points make a line. If we want to extrapolate to 11, you fill out the same formula, use the same slope-intercept form, and extrapolate. And usually I like to graph stuff and make sure that I'm put a couple of points together to make sure I'm not making a math error. It's usually final minus initial, or right versus left. And the only one is, in this case, x is the variable of interest. Like, are we checking at x equals 11? But extrapolation can be very dangerous because your model is often not valid beyond the bounds of data you have. It's especially bad for noisy data to do extrapolation. So things can change if you extrapolate beyond 10. Maybe you have a phase change, maybe your patient dies, whatever. There's issues with extrapolation in many cases. And if you look on the other end, going at 0.5, you're trying to extrapolate down. Again, the whole idea is using the left data point and the right data point. Make a line, and then in this case, your left data point is still 1, so you're subtracting 0.5 minus 1, you're going to get a negative value. So you're going off of this. This is your point, you get your slope between the 2 points, and you're extrapolating down. Again, make a graph of your 2 or 3 points that you're interested in, just to make sure you don't get something flip-flopped if you ever have to do interpolation or extrapolation.